Hi class, today we are going to study about 5.2, the definite integral. So I want you to understand that yesterday or the previous lecture, what integral means. If you have a function, if any function you have, and this means find the area. And how we approach this one is by graphing. And then this case, you can actually make a left-hand sum, right-hand sum. We call it as a Riemann sum. And we get to find the area. This one as a triangle, actually, we can actually find easily. But if it's a something function other than that, it's not going to be easy. So that's what I want to actually tell you about the beauty of the calculus. Finding the area has been really difficult before 17th centuries. Like only areas that you can actually find, if you can really think about it, you can only do rectangle, square, triangle, circles, or some of the trapezoid. Those are the ones that we only learn through K through 12. But if you are in calculus, now you can find the area, anything, if you have an equation under the equation. So anything under the curve, we can find the area. That's the actually huge beauty of the calculus. And then that actually discovered in 17th century. I feel like it's discovered by Isaac Newton's mentor. Yeah, his name is Isaac too, but I don't know the last name. But his mentor was the person that actually discovered the integrals. So let's continue study. So last time we talked about it, as we see this function is 1 over t, then we want to find the area under, then we are going to take an integral, and then how we rewrite this one expression as 1 to 2 respect to dt. So I want you to understand integral means just to find the area. Okay, and from 1 to 2 over here. Later on, you're going to see that this is going to be y and this is going to be x, because this is going to be f over x as your function, and that's going to be your value in the bottom of your differences. So that's going to be your area. So this case, we see n as a 2, but whenever you're making your rectangle more and more, this one has n as 10. Still, it's the same function, but I made my rectangle more, then as you see, my arrow is going to be a lot smaller. So if I'm making my n as infinity, that becomes actually this notation, which I will explain on our main dish. And from 1 to 2 of the function 1 over t, and then I'm going to find the area under this curve. So you can basically think as this one is height times base. Height times base, I'm going to have so many of them from 1 to 2. So please try to listen all my explanations, because that will make it so much easier. And then let's look at our appetizer first. So let's talk about our appetizer 1. So we are going to repeat similar procedure as what we did previous section, and then I'm going to explain some more details and how we can build the integral notation from the Riemann sum of adding all those rectangles. So look at here, we are going to also have left hand sum and right hand sum again, we call it Riemann sum, and it's 2 of this function. So understand, I want to find the area from 1 to 2 of the function of 1 over t. So 1 over t, we know that function, I'm going to actually increase my scale as 1, 2, 1, 2 here. So by plugging, you can also plug in x and y as 1 over x. Plugging 1 gives me 1, 2 gives me 1 over 2, and then 1 over 2 gives me 2, so that I can connect my function this way. And then as a odd function, there's also other side in here. So from here, what I want to see is I want to find the area from 1 to 2, and then I'm using n size as a 2. So in this one, dividing by 2. So that's what I have. Then one by one, this rectangle, if I draw with my different color, left hand side means I'm using left side as my height. So my rectangle will be this shape, as you see, overestimated. Next one, my height is left here, so that is going to be my rectangle. So look at my base is going to be, we call it as a delta x. How we get this one? 2 minus 1 divided by n, which is 1 over 2. So our delta x is 0.5. Some of you guys just see automatically. Yeah, that's totally like I do that too. So base is 1 over 2. Height, careful, this function input 1, and that is 1 over x function, right? Actually 1 over t function. So if I plug in 1, and it's going to be 1 over 1, so my height here is 1. So I will just put 1 comma 1. And then if I plug in 1.5, which is 3 over 2, right? So if you plug in 3 over 2, which is 1 over 3 over 2, 1.5, which means 1 divided by 3 over 2, 1 multiplied by 2 over 3, those who forgot some algebra, that becomes 2 over 3. So that's 2 over 3. Since I have only 2 rectangles, these are the values I need. So my base 1 over 2, height 1. My base 1 over 2, now height is going to be 2 over 3 at your x value is 3 over 2, which is 1.5. So from here, I know I explain very slowly, but it's important for you to understand. That's why that will make 3 over 3, so 5 over 3. So total 5 over 6. So my number, if you punch into calculator, let's see, because sometimes it's nice to fill it. I get 0.8333. So that's what I got as a left-hand sum. Now let's check this one with our notation. Okay, so I'm going to rewrite this one as a mathematical notation, and I want you to look at this one carefully. So this point, I'm going to call it a point 0. This one is a point first one. This one is a point second one. Okay, because that's where I'm gonna plug in. So carefully look at here. I'm going to multiply delta x, which is a base, times f of sub 0 of the x value I plug in, plus and plug in f over 1, and those are two values. So how do we write this one? And we are going to write as, later on you're gonna have so many expressions, could be like 100 of them. So we write that as a sigma. So imagine that you have like f over like 100. Then I write it as I started from 0 to, you are going to end at right before f2. So if you have 2 of them, you're gonna end at 1 minus, and then 1, and then f of your function x, and then I is going to be here. So that's going to be your height times base is going to be delta x for everything. That's your base. So understand here, everything is a height times base. Then this means add. Just we use as the notation, add. So what's gonna happen later on? This we are going to send limit. I'm talking about basically main dish, and I'm going to explain one more time there. So I wanna have more than 2 as my dish. I wanna have infinite many. So we are going to send that n size has infinitely many. Then what's gonna happen later? So many rectangle that it has to be illusion of, so under the curve that becomes integral of f over x times dx. Just understand this big picture. I will tell you the explanation one more time. So look at this one again. Right hand sum. Right hand sum is going to be same graph, and as you guys have been practiced, I'll go a little bit faster. So right hand sum here to here, and that's going to be n size as a 2. I'm going to use this one and this one as my height. So this time my value is going to be underestimated. First one we call it f0, and this one is f1, and this one is f2. So that's how we count. Like here it's going to be 0, 1, 2, 3. So that's 0, 1, 2. And then I'm going to find the area of this under the curve 1 over x. And then we are going to write it 1 over 2 as my base size. And then height, I'm going to use f of 1, which is, this point is 1.5, 3 over 2. So if I plug in 1 over x again, that becomes, we saw that 3 over 2 becomes 2 over 3, right? Plus, that's the height after I plug in. And the next one is going to be, value is going to be 2, because I'm starting from 1. So 1 over 2, and my height as 2. 1 over 2 is going to be now my height for this one. All you need to do is just find the coordinate if you get confused. And that's the height, that's the basically where x coordinate is. So pull out by 1 over 2, and then you can make a common denominator as 4 over 6 plus 3 over 6. Then it makes 7 over 12. So let's punch into calculator again. That makes 7 divided by 12. I get 50 0.583. Okay, so I like to find the area under 1 over x. This gave me 0.83, and which as overestimated, and then right hand sum gave me underestimated as a 53583. So now if I want to find the area, we can actually find the average. So 0.83 and 0.583 and divide by 2. That will give me 0.706. Yeah, that's what I get. Okay. But I'm going to explain this one more time. I know you're going to be confused, so I'm going to explain here and then one more time after. So I'm going to formalize this one. So my base is going to be always delta x. So delta x times my height f over 0 plus delta, oh, this time it's going to be 1 because that's my height I'm using. And delta x base times height f over 2. So summarize this one, factor out by delta x and then f1 plus f2. And later on, we're gonna have not f2, like you're gonna do as in-class activities, and as 4, but it will be 8, 10, 20, and 100. So whenever it gets more, you don't want to list all those numbers out. So we can use the symbol, add those numbers. That's the symbol we're using, and then the function f over x, index I, and then base is going to be delta x from I is starting from this time 1 to 2. So that's how we write it. And then after resending, this one is a limit. This expression is going to be, and goes to limit so many rectangles, it becomes integral 1 over x, which is your function, times dx as your base. So just remember this one, and I will show you again. But now, you guys remember what will make a derivative as 1 over x? What will make derivative as 1 over x? Do you guys remember what will be antiderivative? Yeah, it becomes from natural log of x. If you take a derivative of natural log x, that becomes 1 over x. So how we usually compute, this is actually the next session, but I will just show you quickly. From here 1 to 2, all you need to do is natural log of 2 minus the natural log of 1, but I know the natural log of 1 is a 0, so my answer natural log of 2. So I want to compare that natural log of 2, what would that be? I got 0.693. So we're just using rectangle estimation of the average of those two. At that time in 17th century, that was actually really good estimation, right? So I want you to actually feel that now we have a calculator and the Desmos and all those resources, and that we can actually use it. But at that time, this was a very important fact. I really hope that you see the beauty of the calculus, and then I wanted to continue your in-class activities, exactly same thing, but n size as 4, so you're just gonna have the same thing with 4 of them, and then compare the answer with me. Good job, it was a long one. Okay, so let's compare our in-class activities together. So if I have a 1 over t, instead of using n as 2, I'm going to have n as 4, which means in 1 divided by 4, so my delta x is 1/4, and then I'm gonna have 4 rectangles here. So all the base is 1/4, and then my height will be my y value in here. So as you see, that's what I get. Factor out by here, and then you can do by hand too. So I got the number 0.759 as area. So as you see now, n size is 4. My estimation is getting closer to my answer. So if I want to write this one as my sigma notation, then look at here. I said everything is going to be base times height. So you have a delta x times function f over x. Then you have 1, 2, 3, 4. So we have to indicate that as I. I started from 0 to 3. Why is it 0 to 3? We count the number here, 0, 1, 2, 3. In the coordinate system. So here is 0, 1, 2, 3. So those are the 4 rectangles as height I'm counting. So this one, after we are going to send the limit as infinity. In main dish, we are going to show you that n as infinity. We are going to have this become the integral f over x times dx. Basically, this is the same thing, and then this is the same thing. You're gonna see I'm going to repeat again. So adding all those rectangle with rectangle, how many? Infinitely many becomes the integral notation. Okay, so let's look at right hand sum again. That will be our underestimate. And as you see, I have 1, 2, 3, 4 rectangles. So 1, 2, 3, 4 rectangles, and then you can use this one as your height here. So factor out and then punch into calculator. So when I have n as 4, now my estimation got 6, 3, 4, 5. So as you could guess, whenever you have more n size as like 100, n size as 100, and making left hand sum, right hand sum, my number is gonna be closer to 0.69, which when we set n as infinity, so that sigma becomes now integral when it goes to infinity. Okay, so if I write this one as a notation, look at this one carefully too. Base times height, so my height is f of x, base is dx, and then why is it dx? Because my delta x also become very tiny, teeny, that is looks so teeny, just look like a dot. So height and base, and now what's going to be my I? I is going to be sending from 1 to 4, because this is going to be right hand sum, get used to it, and then that's my sigma notation. So if you don't want to write this whole thing, that's how we write it in mathematics. And then one more time, if you're sending limit, that becomes the integral of f of x times dx. Okay, so let's do the main dish. Okay, so on my main dish, I'm going to explain how the sum of the rectangle becomes the integral. And if you saw the appetizer part, I explained seriously more than 50% here. So let's just do one more time so that it becomes better you to understand. So here says, now I want to describe in general way of finding the area under the curve. So here's a function called as f of x. Then don't forget all those coordinates here, that's going to be input x0 and output f of 0, right? So we can write it this way, or you can write it a and then f of a, same thing in this case. And if you see n is going to be number of rectangles, like n as 5, n as 100, like we've been playing some of them like this. And then delta x represents the base length. So just think that this is going to be delta x. Then let's try to find the left hand sum. So all we want to do is how we find the Riemann sum in here. So look at your graph carefully. My left hand sum will be over or underestimate. Do you see that it's going to be overestimate? So this is going to be first one. So I'm going to write base is delta x, and then what is the height, which we write it as f over 0x, plus next one, if you can do it together with me, and that's the coordinate I have to find. So x over 1 comma f over 1, or you can actually write it f over x1. That's probably what we write. And delta x as a base, and then height is going to be x as x1, because that's going to be your input. And continue. Next one, now do you see the pattern, right? So f over input as x2. So delta x times f over x2. Then how far do we have to go? Do we have to go all the way to x to n, or do we have to go x n minus 1? Since it's going to be left hand sum, you are going to end here. And here to here, you are going to have a total n numbers of a rectangle. So this is the rectangle that I want to find as the last. Delta x as a base, and my height is going to be xn minus 1. So now we have so many of them that we can rewrite this one as a simple way. How we write it? Add them all. The pattern is delta x times f over x. And then I saw that numbers are different, so we just put as I. Then what is the I? Starting from 0 to n minus 1. There you go. So that's how we write this whole long thing into this way. You know, actually, I was in downtown when I came to San Francisco working in a company. We use this one actually at work. So I want you to just not exactly finding the area, but we use for the Excel and then actually finding all those sums. So now I want you to try together with me right hand sum. This time, if you break it down, delta x times my new height is going to be x1, delta x, and then f over x2, and then delta x, f over x3, and how far is it gonna go? Delta x and f over, this time it's going to be up to xn, right? It's gonna end here as my right hand sum. That's going to be my right hand sum. So where my right hand sum ends, it ends at x of n. So we rewrite this one whole thing is too long to write. My life's too short. So I'm gonna write it as function times delta x, and from I starting from where to where? 1 to n this time. So that's how we write it as a Riemann sum over here. So class, let's just summarize what I just talked about previous. So previously, all those rectangles, when you add it, as you see, it becomes this notation. Do you Notice that where we saw this one, it's right here, right? Same thing. And then next one, if you look at this, so you saw it right here as our right hand sum, exactly same notation. Then if we sending limit as n as infinity, why? Because instead of having 1 through 0 through 1 rectangle or 0 through n rectangle, I want to have many possible instead of 4, 8, 10, 100. So sending it, that becomes area under the curve a to the b, same notation, height times base, height times base. Here is going to be your height times base. And then right hand sum, same idea, and then you get that, and then that becomes this one. So what happened? Whenever you have an n size so big that you are going to eventually have same number. Let's just say as a limit. I wouldn't say that same number, but it's so close that my limit actually goes to that one certain number. So this one we call as definite integral. Definite integral always has domain from A to B, and then there's also indefinite integral. That means we do not have those area. So sometimes we want to find the area here to here, but I want to find the area actually whole thing. Then this time we call it indefinite integral. This one is definite integral. So I want you to understand the two differences. So okay, that's we call as a Riemann sum. Don't forget that word. And then now you see that how Riemann sum connected to the integral here. Okay, so now on our dessert, let's keep studying about what integral means. So let's look at this function. How does a definite integral this relate to the area between parabola x squared minus 1 and x-axis? So this means, break it down. I have a function. Do we know that graph? Yes, x squared minus 1 is x squared, and then shift it down 1. So I'm going to have my graph shape, this, which is x squared minus 1. Then here says, find the area under the curve x squared minus 1 from negative 1 to 1. Negative 1 to 1. So this represents the area right here. Then how are we going to find the area? So I'm going to actually show you how we're going to find the area mathematically. First, integral negative 1 to 1 x squared minus 1 dx. As this number actually came from our antiderivative. So I want you to guess. This time I just want to do it for you. So I'm guessing that as this. And then what does that mean? I want you to take a derivative of this one. Do you get this guy? Right? If you take a derivative, if you get that one, that's what you call as antiderivative, which is the same as the integral from negative 1 to 1. So how we compute this one? 1 over 3, we are going to plug in. 1 cube is 1 minus 1. And then subtract those two values. So I plug in this, and I plug in negative 1, and then subtract each other. So let's simplify. I have 1/3 minus 1 minus, this is going to be negative 1/3 plus 1. So if I rewrite this one, 1/3 minus 1 plus 1/3 minus 1. So 2/3 plus 2. Almost there. And that's going to be, that's minus 2. So 6 over 3 minus, I get 4 over 3 as a negative. So you can see that each piece, this one is actually 2/3. Is it pretty cool? Yeah. So if you have a graph here, this is a 2/3. Then this is 2/3. So together makes negative 4 over 3. Why did we get negative? Because your graph is under the x-axis. If your graph is under the x-axis, we call as area is negative. If it's above, then it's going to be positive as area. So that's how we actually compute in algebraically using integral. But now I want you to actually try Desmos if you can punch in. Honestly, I do not have internet right this moment. I know, right? Yeah. So I do not have it right this moment. So I want you to actually look at my figure and then try to follow here. I will just show you where you can go. So open up your Desmos. First, open up your Desmos. And so do you see this button right here? So if you click this one, then you get to see all those graphing calculator functions. Then click functions, then go all the way to miscellaneous. And if you look at, you see that there's an integral you can actually put in. So click that, and then from here just copy down, copy down. So I hope that you can follow the instruction, then copy down, and I will go back here. So Desmos, I want you to go open this keypad, and then there's a function, and then there's a key for, I don't know actually how to read it. Then you will see that there's an integral notation, and when you say type everything up to dx, and then try to see that if you got the same answer as a -4/3. I'm so sorry I cannot show you the answer there, but if you type in this one, then you will get the exactly same answer, or they probably put it as decimals, which will be 1.333 negative, right? Okay, so I want you to do in-class activities. You can use the decimals. So this section 5.2, 5.3, 5.4, you can actually use decimals as your answer, and then homework, they're not going to indicate that you have to use a calculator, but you can use the calculator or decimals as well. So please utilize so that you don't get frustrated. Then let's look at our activities. So class, now we want to find the integral of -1 to 1 in square root of 1 minus x squared. So we want to find what does that mean as area, and then find exact value. Also, we are going to use a calculator or computer to compute. So when you look at this one, I have no idea what this will be, right? So I want you to open up your Desmos again, but this time instead of using integral, could you just type this whole thing? So type this whole thing and look at the graph. Do you see it as a graph? What is a graph? Your graph is going to be circle with radius 1. Did you get the same one? Why? Because square root of 1 minus x squared is equal to y. If you square it both sides, I get this. Then 1 is equal to x squared plus y squared. So basically this is the shape of this circle, half circle. So I want you to actually recognize this one. It will pop up a lot in calculus 2 as well. So they're saying that find the integral, find the area from -1 to 1. So I want you to actually find the area using algebraically. How do we find the area? Pi r squared. My radius is 1, so my answer is a pi. And then don't forget, we have to divide by 2 since it's a half circle. So my value is pi over 2, which is 1.5 something, right? Then now I want you to see the graph was a circle. First, I want you to have a whoa. I wish that you recognize it. And then I want you to type this one on the next line and as follow the instruction that I show it to you. And thus this value get exactly same as pi over 2. And yes, that's what you will get. So just to see and get used to how you use the Desmos, and then make sure when you use the homework, I want you to also use the Desmos. Yeah, a lot of them you probably have to use it, and I'm okay with that. So class, let's look at our dessert. The dessert will be pretty delicious. So we like to see how this function look like. For me, when I look at it, I could not even guess. So I want you to actually find the total area under the curve from 0 to the square root of 2 pi. No clue, right? So what I want you to do, follow my instruction carefully. So I want you to open up desmos.com, and then I want you to copy everything. I want you to just copy everything. This number, and here I want you to write your name so that you did it. And then this number, just with using everything, I want you to copy 1 through 8. And as I tried to say, this number, you can just put as a 0 and B as a 0. That's totally fine. That will generate the slider here for you. So copy everything on the Desmos, and it will be homework as your in-class activities. So please do so. If you do this one, your in-class activity will be very easy. So if you utilize with the Desmos, you see that the area between 0 to the square root of x, 0 to the square root of x, this is the square root of x. Then I found the area under the curve is 0.894. Then, as we mentioned, now we want to find the area from square root of x to square root 2 pi, not x pi, right? So sorry, I read as x. So square root 2 pi. Then since it's below the x-axis, as you guess, my area will indicate as a negative number. So if you see this one, Now I want to find the total area from here to here. So what should I do? Which will be 0.894, and adding this one will be minus 0.464. So if I punch into the calculator, or I think I can do mentally, 464, if you subtract, that's going to be 0.4. Okay, so I get the area from here to here as a 0.43. Yeah, so that's the answer for total area. But if you want to find the net area, then you want to add this one and the absolute value with that number. Okay, so that's our these are two. And as I mentioned, yes, I want you to use a calculator, and then some of the one that you can use without the calculator, of course I want you to do it by hand. So let's do in-class activities together. Okay, before we do in-class activities, now we have an extra credit chance. Please help me. So when I was setting up the command, I actually get to see highlight from here to here. You probably will be able to do it if you copy everything down in here. Then this is square root of pi, and this is square root of 2 pi. Somehow, I don't know how to shade it below here. So those who can help me to shade under the curve of the x-axis for the area, I will give you 5 points for adding into your final exam. So please help me, and then I think it'll be really good. Class, seriously, this one I just learned last night. So none of those one I know how to do it, and then I just play. So I want to also do it because some of you guys will do actually better than me. So please help me. So in this last in-class activities of our dessert, I want you to actually upload it separately from appetizer. And all you need to do, if you did previous one, same as mine, just change to x cubed. Definitely their graph will be the different. And I want to type everything in line to previous one, and then just change to x cubed function and see that how function look like. So you are going to upload in class activity 3, and it's going to be zip file, right, or one of those photo files. The reason I want to make it separately, it's easier to just you can put the photos, and then those who did extra credit also just put it, either you can put it separately or you can just make one file together and put it together. I can totally read it what you did. And don't forget, put your name on it wherever you can find the spot where I can find your name on. So screenshot and then upload it, not on the appetizer. I will make a link YouTube, put the in-class activities of the Desmos activity. So good luck, and then this is it for 5.2.